This is Module 7 of Applications in Engineering Mechanics. Today we're going to make use of the method of joints, or sometimes called the method of pins, to analyze truss structures. Here's a truss that we're going to look at, and we're going to find the forces in all of the members of this truss. And we're going to use the method of joints, which I talked about last time. And this is the rules for cutting through trusses. So we're going to isolate one joint. I'm going to go ahead and start off by isolating this joint at B. I'm going to cut through each member only once. And I don't cut through the joint itself. I continue to cut to isolate the entire portion within the circle. And I'm going to assume tension in each of the cut members. So here is a free body diagram of joint B. So I've got an external reaction here, By, from the roller, and I'm going to assume tension in FBC and tension in FBE. And from geometry, I see that this is a 4 on 3 slope. There you go. 4 high, 3 vertically or horizontally. Okay, so that's my free body diagram. Since I do have an external reaction in that free body diagram, I'm going to have to solve for it. So I'll do that by solving the entire structure's free body diagram. So let's do that together. I've got FBY. I've got a pin over here, so I'm going to have AX and AY. For the force that's in the joint B, I only need BY, but let's go ahead and solve for AX and AY as well, since I'm going to eventually need those as well. So let's begin by using the equation of summing the moments about A, setting it equal to 0. I'll call counterclockwise positive. And I'm going to have -1 times its moment arm, which is 3. -3 times its moment arm, which is 6. -2 times its moment arm, which is 4. Plus BY times its moment arm, which is 12. And that's going to equal 0. And so what that gives me is BY ends up equaling 2.42. And it's positive, so BY is 2.42 kips up on the truss. As I said, that's all I would need to go back and solve for joint B's free body diagram. But let's go ahead and solve for AX and AY because we'll use those later. So I'm going to sum forces in the X direction to find AX. I'll choose to the right positive. I've got AX, and the only other X component force I have is 2 kips, so it's +2 equals 0. So AX equals -2. So instead of to the right, AX is actually to the left. And then finally, I have to solve for AY. I'll sum forces in the Y direction. Choose up positive. And I get, let's see, AY -1 -3 plus 2.42 equals 0, or AY equals 1.58. So AY is 1.58 kips up, and we'll use that later on. Okay, so now we can go back to our free body diagram of joint B. I put in the BY of 2.42, and we can now use the equations of equilibrium to solve for our first two members, FCB and FEB. So let's sum forces in the Y direction. I'm doing a lot of this together with you, but pretty soon here I'm going to let you take off and do it on your own, since It just gets to be the same procedure over and over again. So we've got the 4/5 component of FCB plus 2.42 for the BY equals 0. And so I get FCB equaling minus 3.025, which that means that instead of tension, I assume them all the members in tension, but instead of tension, this member is in compression. So FCB is equal to 3.025 kips in compression. And I'll just put the symbol C in parentheses there for compression. So that's one of my forces in one of my members. Keep on going. Let's do some of the forces in the X direction. Set it equal to 0. And I've got minus FEB minus 3/5 of FCB equals 0. Substituting, we found that FCB was equal to minus 3.025. And so that gives us FCB equals FBC, SCB, same thing, 1.815. And it's positive, so that means that member is in tension. FCB is equal to 1.815 kips in tension. So now we've gotten two of the members. So we're just going to keep on going now. We've taken care of this member and this member. Let's go ahead now and isolate another joint. I'll go ahead and choose to isolate joint C. We're going to need to draw a free body diagram there. We know that the force in member BC or CB is 3.025 kips in compression. So I'm going to draw that like that. And we don't know these other two members, so we're going to assume them in tension. So this is going to be FCD and FCE. That's a good free body diagram. And we can go on from there. So here we go. There's joint C. What I'd like you to do now is to sum forces in the X and Y direction and come up with the force in members EC and DC. If you sum forces in the Y, that's the answer that you should have gotten for FEC. Now I'd like you to go ahead and sum forces in the X to get the forces in DC. There's the answer for the forces in DC. You should go through it step by step on your own. So now we have this member and this member and this member and this member done. We've got to go to another joint. We keep going, method of joints, one at a time. So let's go through here. And for this one, we just found out that from the isolation of joint B that member FBE or EB is 1.815 in tension. We just found on this free body diagram that FCE is 3.025 in tension. We have 3 kips down at point E. We don't know what these two forces are, so we're going to assume them in tension. And we're going to go ahead and analyze that joint. So please go ahead and do that on your own. So here's joint E with the sum of the forces in the X and the sum of the forces in the Y direction. And so now let's total up. We've got this member, this member, this member, this member. So we're going to do that joint D next. And so for joint D, 1 kip force down at the pin or at the joint itself, D. We just found out from analyzing joint C that member CD is in compression, and it was 1.63 kips in compression. Then we have FDE Here it is, 0.0725 in tension. This is unknown, so we'll just call that FAD. That's a free body diagram of joint D. And here is joint D. And, oh, I forgot to put in, no, I put them all in. And now I sum forces in the Y direction. I can find FAD. You actually only have to do one of these equations. I've double-checked by doing some of the forces in the X direction and find that that also gives me the same answer for FAD. So FAD is 1.975 in compression. So now we've actually gotten all the members. We can do one more check by isolating joint A and make sure that the values that we found for FAD and FAE are correct. So if you'll do that on your own, double check. I'll just show you the answers on the next slide. So there you go. I've double checked joint A. I found out the external reaction, if you go all the way back to the free body diagram of the entire structure, was 2 kips to the left. Here's my other members. If I sum forces in the X and the Y direction, I get 0 equals 0, and so the structure checks. So we've taken care of the force in every one of the members of this truss. So let's go ahead and have you do one on your own. Here's a truss where you can analyze using the method of joints, and I've got the solution in the module handouts. And we'll see you next time.